Ever pondered about the mysteries of our universe? What if we told you that ripples in the fabric of space-time, known as gravitational waves, hold many of these answers? Gravitational waves, invisible yet immensely powerful, are disturbances in the curvature of space-time caused by accelerated masses. They travel at the speed of light, carrying with them information about their cataclysmic origins. This concept might seem like something out of a science fiction novel, but it's actually a cornerstone of Albert Einstein's theory of general relativity. In 1916, Einstein predicted the existence of these waves, describing them as ripples propagating through the space-time fabric. For nearly a century, these waves remained theoretical, eluding direct detection, but science has a way of turning theory into reality. And so, gravitational waves shifted from the realm of theoretical physics into the tangible universe, opening up new ways to observe and understand the cosmos. Gravitational waves, once a theoretical prediction, now a groundbreaking reality. To understand gravitational waves, we must first visit the mind of Albert Einstein. He rocked the scientific world with his general theory of relativity way back in 1915. This theory was revolutionary, transforming our understanding of the very fabric of the universe. In Einstein's universe, space and time are woven together into a four-dimensional fabric known as space-time. This fabric isn't static. It's dynamic, bending, and stretching under the influence of mass and energy. So, when an apple falls from a tree, it's not because of some invisible force pulling it down. It's simply following the curvature of space-time caused by Earth's mass. This was a groundbreaking shift from the Newtonian idea of gravity as a force acting at a distance. Einstein's genius lay in redefining gravity not as a force, but as the result of the curvature of space-time. Einstein's theory set the stage for the prediction of these elusive gravitational waves. Einstein's equations, complex as they may be, hinted at something extraordinary. Nestled within the intricate mathematics of his general theory of relativity, Einstein predicted the existence of gravitational waves. These are not waves in the traditional sense, like waves on the ocean or sound waves in the air. Instead, imagine them as ripples propagating through the very fabric of space-time. According to Einstein's equations, massive objects in motion, like spiraling binary star systems or colliding black holes, would generate these ripples. Think of it like tossing a stone into a pond. The stone disturbs the water, creating waves that radiate outward. In a similar fashion, massive cosmic events send gravitational waves rippling across the universe. These waves carry with them information about the dynamics of the massive objects that created them. The stage was set, but the hunt for these waves was only just beginning. Enter LIGO and Virgo, state-of-the-art observatories designed to detect these space-time ripples. The Laser Interferometer Gravitational Wave Observatory, or LIGO for short, and its European counterpart Virgo, are the masterminds behind the detection of gravitational waves. But what makes these observatories so special? Let's delve a little deeper. Both LIGO and Virgo use a method called laser interferometry to measure the incredibly tiny distortions in spacetime caused by passing gravitational waves. Imagine a pair of long arms at right angles to each other, each several kilometers long. At the end of each arm, a mirror reflects a laser beam back to the starting point. When a gravitational wave passes through, it stretches space in one direction and shrinks it in the other. This causes the laser beams to travel different distances, creating an interference pattern that can be measured. LIGO consists of two such observatories, one in Louisiana and the other in Washington state, allowing for cross-verification of detections. Virgo, located in Italy, adds a third point of reference, significantly improving the ability to locate the source of detected waves in the sky. These observatories are not just large-scale science experiments, but are triumphs of engineering. They have to be incredibly sensitive to detect the minute changes caused by gravitational waves, yet also incredibly robust to ignore all the other possible sources of noise, from earthquakes to traffic. Indeed, the changes they measure are smaller than 1/10,000th the diameter of a proton. The anticipation was high, the stakes even higher, and these observatories did not disappoint. After decades of development and refinement, LIGO and Virgo were ready to listen to the symphony of the cosmos, to detect the elusive gravitational waves that would open a new window into our universe. These remarkable observatories would soon make history. On September 14, 2015, a century-old prediction was confirmed. The world of science was abuzz with excitement as gravitational waves, predicted by Albert Einstein's general theory of relativity, were detected for the first time. This monumental achievement was the result of decades of tireless effort, ingenuity, and the unwavering belief that these elusive ripples in the fabric of space-time could indeed be captured. The heroes of this historic moment were the observatories of the Laser Interferometer Gravitational Wave Observatory, or LIGO, as it is more commonly known. Nestled in the heart of the United States, these twin observatories, one in Washington and the other in Louisiana, were designed to detect minute distortions in space-time caused by passing gravitational waves. The waves detected by LIGO originated from a violent cosmic event, a collision between two black holes, each about 30 times the mass of our Sun, occurring approximately 1.3 billion light-years away. This cataclysmic event, a binary black hole merger, created ripples in spacetime that traveled across the universe, finally reaching our planet. The gravitational waves from this event stretched and squeezed spacetime as they passed, causing the arms of the LIGO detectors to minutely change length. These changes, smaller than the size of a proton, were picked up by LIGO's incredibly sensitive instruments, confirming the existence of gravitational waves. But why was this detection so significant? Well, gravitational waves give us an entirely new way to observe the universe. Instead of relying solely on light and other forms of electromagnetic radiation, we can now listen to the universe through these gravitational whispers. This opens up a whole new window to study the cosmos and promises to unlock secrets about the nature of gravity, black holes, neutron stars, and perhaps even the origins of the universe itself. This was a game changer, the dawn of a new era in astronomy. With this groundbreaking discovery, we've taken our first steps into the uncharted territory of gravitational wave astronomy. And who knows what incredible discoveries await us as we tune into the symphony of the cosmos. But what do these gravitational waves tell us? Well, they speak volumes about the universe's most dramatic events. Each wave has unique characteristics like polarization and frequency, which are immensely informative. Polarization describes the wave's orientation, revealing the nature of the cosmic dance that generated the wave. Frequency, on the other hand, is determined by the size and velocity of the event. Larger events produce lower frequencies, while smaller, faster ones result in higher frequencies. In other words, by analyzing these characteristics, scientists can decode the messages carried by gravitational waves, learning about the size, shape, and dynamics of their source. These waves are like whispers from the cosmos, telling us stories of black holes colliding, neutron stars merging, and possibly many other phenomena we haven't even discovered yet. Each gravitational wave carries a unique cosmic fingerprint. Gravitational waves have opened a new window into the darkest corners of the universe, black holes. These cosmic behemoths, with gravity so powerful that not even light can escape their grip, have long fascinated and perplexed scientists. But it is through the lens of gravitational waves that we can truly begin to understand them. When two black holes spiral towards each other and eventually merge, they send out ripples in the fabric of space-time. These ripples, or gravitational waves, carry with them information about the cataclysmic event that produced them. They tell us about the mass and spin of the black holes and the energy released during the merger. It is as if we are listening to the symphony of the cosmos, with each black hole merger playing a unique note. But how do we listen to these gravitational waves? Enter the Laser Interferometer Gravitational Wave Observatory, or LIGO, and its European counterpart Virgo. These observatories are designed to detect the minuscule distortions in space-time caused by passing gravitational waves. The detectors act like cosmic microphones, picking up the faint whispers of black holes from billions of light-years away. The first detection of gravitational waves in 2015 confirmed that black holes do merge, validating a key prediction of Einstein's general theory of relativity. It was a momentous discovery, akin to hearing the universe for the first time. But more than that, it marked the beginning of a new era in astronomy. an era where we could study black holes and other celestial phenomena through the lens of gravitational waves. The study of gravitational waves and black holes is still in its infancy. There's much we have yet to learn about these cosmic juggernauts. But with each new detection, we peel back another layer of the black hole mystery. Through the language of gravitational waves, we're beginning to decipher the story of black holes, their births, their lives, and their cataclysmic deaths. Through gravitational waves, black holes are no longer shrouded in complete mystery. The quest to understand our universe doesn't stop here. With the detection of gravitational waves, scientists recognized the need for even more precise instruments. This led to the development of advanced LIGO, a second-generation gravitational wave detector. It boasts a 4-fold increase in sensitivity, enabling us to peer deeper into the cosmos than ever before. But the upgrades don't stop at sensitivity. Advanced LIGO also has an improved frequency range, which allows us to detect gravitational waves from a wider variety of cosmic events. This is like tuning into more channels on your radio, each one playing a different symphony of the cosmos. The future holds even more exciting possibilities. Scientists are already planning third-generation detectors such as the Einstein Telescope and Cosmic Explorer. These observatories will be 10 times more sensitive than advanced LIGO, allowing us to detect gravitational waves from the dawn of the universe. And let's not forget about LISA, the Laser Interferometer Space Antenna. This space-based observatory will be free from the noise and limitations of Earth-based detectors, opening up a whole new window into the universe. With each technological advancement, we edge closer to decoding the universe's secrets. These future upgrades and new detectors will allow us to listen to the universe's gravitational symphony in unprecedented detail, and who knows what we might discover. The detection of gravitational waves is a testament to human ingenuity and curiosity. This groundbreaking discovery has opened up a new way of observing the universe, ushering in an era of gravitational wave astronomy. It has validated Einstein's century-old prediction, reinforcing the robustness of the general theory of relativity. Gravitational waves have given us a fresh perspective on the universe's most violent events. They've allowed us to witness the merger of black holes, an event previously thought impossible to observe. They've provided us with the first direct evidence of binary neutron star mergers, opening up the field of multi-messenger astronomy. The detection of these space-time ripples has also offered us a new tool to test the limits of general relativity, probe the nature of black holes, and investigate the properties of neutron stars. These scientific breakthroughs have been rewarded by the international scientific community, with the 2017 Nobel Prize in Physics awarded to Rainer Weiss, Kip Thorne, and Barry Barish for their decisive contributions to the LIGO detector and the observation of gravitational waves. The exploration of gravitational waves marks a significant milestone in our quest to unravel the mysteries of the universe. It's much like being given a new sense, enabling us to hear the symphony of the cosmos. From a ripple in space-time to a leap in our understanding, the discovery of gravitational waves has indeed been a cosmic journey.